Hey, today we're going to talk about not only Newton's second law of motion, but also the first. First is a little less complicated because there is not really much for math on the thing, but the second law gets a little bit hairier with the net force and so on. So we'll get to that in just a moment. So let's just take off with, hey, Space Shuttle Endeavour. So it turns out to get to the moon, Newton's laws work fabulously. Um, Things aren't exactly spot on with a lot of things. Like it does, sometimes the Newton's laws don't work quite as well when you talk about the quantum nature of things, really small things, especially if small things are moving fast. But for the most part, it works great for getting around and doing what we do day to day and so on. So here we go. We're going to talk about the laws of motion, inertia, action, reaction, and acceleration, all that fun stuff. All right, so after this module, I'm going to split this module up a little bit so it's a whole lot to take in all at once. Okay, we're going to be able to write Newton's second law. I'm going to call that FMA here in a little bit, and talking about units of mass, force, and acceleration, because that's what your lab that you just completed was all about, actually. But first, we're going to learn about this mass versus weight, because there's a lot of misunderstandings about the difference between the two, because they are not the same thing. And we're going to stress free body diagrams. We're going to draw a lot of those clear up to the holiday. And even after the holiday, we'll keep on doing it. But we're going to do for the next month, we're going to do a load of free body diagrams. And we're going to apply this all over the place. Alrighty? The second law here. And the first. And we'll even get some thirds in there. Okay? But right now, first law. Object at rest stays at rest, something in motion stays at motion at a constant speed in a straight line. Because if it curves, that's actually an acceleration because it's a change of velocity. Remember, velocity is two parts. One is the magnitude and one is the direction. So even if you're not changing speed, you're changing the direction. It's still an acceleration. It takes an unbalanced force to do that. That's the second law. Well, this is the first law. In the absence of a net force, things at rest stay there. Things in motion stay in motion. And there really isn't a difference between the two. And if you think about it, right now, are you at rest or are you in motion? The answer is yes. And there's not really a difference between the two, because you're always in motion compared to something. But if you're not changing motion, it doesn't matter whether you're at rest or moving at a constant speed. There's not really a big difference. Say, for instance, you woke up on an airplane and you heard some noises, but how do you know it's not just a fan running? Maybe you're not actually flying in the airplane. How would you know? If everybody has the windows closed, how do you know you're actually flying in the airplane somewhere, or you're already on the ground? The answer is they're so smooth, you really wouldn't know the difference because you're not changing motion until you hit some turbulence. Then it becomes a little more obvious. Okay? Alrighty. So here's a classic example. Yanking out a sheet of paper or tablecloth with stuff on top of there. Things tend to be at rest. You want to stay at rest. Assuming there's low friction or things are pulled fast enough that the friction can't accelerate that thing along with it. So that's why you kind of jerk it quickly. Alrighty? There it is. It was at rest. It's tending to stay at rest. Made a little pop up in the air. Got a little bit of a tug on it because it wasn't completely an unbalanced force on it, but close. So it is, there we go, just what we talked about, in the absence of a net force, or sometimes called a resultant force. A lot of terms going on here. So resultant is the addition of all forces, means they add up to zero. There is no net force. Things will stay at rest or in the motion that they're already in. Alrighty, so if you move these at a constant speed, this is at motion, it tends to stay in motion the whole time. But if the board suddenly stops, that glass is going to want to keep going forward, is the idea. Okay, things in motion tend to stay in motion. Alrighty, so discuss what the driver experiences when you accelerate a car. Well, guys, what happens if maybe put your hands on the steering wheel and somebody's next to you challenging you? They think their car is better than your car, and you got to show them up as soon as that light turns green. So you're getting ready to hit the accelerator. Bam, goes green, and bam, you hit it, and it seems like you're being thrown backwards, doesn't it? You're not being thrown backwards. You're at rest. You're staying at rest. Your seat is shoving you forwards is the key. So there is, when you're in your car and you're accelerating forward, well, that becomes not a first law anymore because you're accelerating. But you get that feeling that something's throwing you back just because there's something pushing you forward is the key. Okay? So that's not really a first law because you're accelerating. Or if you hit your brakes, it feels like you're being thrown forward. You're not being thrown at all. Your body's in motion. It's staying in motion. Okay? So that would be a first law of your body trying to stay in motion going forward, even though there's a net force backwards in the car to slow it down of the wheels gripping the road. So the changes in motion I just talked about, that's really a second law. But the idea is, the reason you get that kind of a throw back, you think you're being thrown back, you're not. Your head's just staying where it used to be. That's your head's at rest, trying to stay at rest, which is a first law, which soon becomes a second law as your body accelerates forward. Alrighty. Driver is forced to move forward, an object at rest tends to... Okay, we just did that. Sorry, it's late at night. I am tired. Driver must resist the change in forward motion of the bike. So, okay, so if something in motion, you stay in motion. We just talked about that. Oh, here we go, guys. Blue car versus a truck. Look at there, guys. So you might say, hey, why is that dude flying out of there? Well, guys, there was an unbalanced force in the car. That's why it slowed down and stopped. But there was not an unbalanced force on the person. Some people think this person's being thrown clean from there's no throwing, guys. Dude was in motion. Dude didn't put a seatbelt on. So there's no force on the dude to stop the motion of the dude along with the car. The car had unbalanced force, which is the second law from the brick wall over here. But the dude having no restraint in motion, you stay in motion at the same speed the car was moving in, flying all over the place. You might say, hey, why is the dude suddenly rotating? Well, that's actually something we learned about in second semester much later in the year, because there was a torque acting on the dude. Otherwise, the dude wouldn't be flipping around like that, because the dude wasn't flipping to start with. But that's a story for another time. So where's the first law in the bottom picture here, guys? It's not the truck, because there's an unbalanced force that stops it, that pushes it backwards to have a negative acceleration on the thing. The first law is that ladder there, going forward. It's also a second law because gravity is accelerating it downward, so it's actually a little bit of both. So things can have both a first and the second law. So in the horizontal direction, that's the first law in the ladder, in motion stays in motion, but it accelerates downward because of an unbalanced force due to gravity. So in reality, we have all these laws happening all the time. All right, guys, I know you're excited for this. It's the Fermat law, where the acceleration is directly proportional to the force, but indirectly proportional to the mass. That means if you were to double the unbalanced force on something, you get double the acceleration. You triple the force on something, you get triple the acceleration. You double the mass, you get half the acceleration with the same force. You triple the mass, you get 1/3 the acceleration because indirectly proportional. This thing right here, that means proportional sign over here. So that's what you guys should have found out in the lab that you guys did last week. Alrighty? So whenever you have a resultant force, that's the F, it produces some kind of an acceleration that is directly proportional to the force, but inversely proportional to the mass. Alrighty, here we go. So let's say we have this person pushing with a force of F. It's going to cause it to accelerate. If you push with 2F, that's twice the acceleration. They're directly proportional. You double the force, you double the acceleration. Okay? 3 times the force is 3 times the acceleration. What if you double the mass? Well, with the same force, doubling the mass is half the acceleration. They're inversely related. So pushing the 2 carts with the same force produces half the acceleration because it's twice the amount of stuff to move. It's inversely proportional. Okay, now we're getting into a whole load of units. I know you guys love the units. The System International, or the international system unit of force, is the Newton. In America, you used to use the pound. Well, the pound is what it is, but a Newton is about 1/5 of a pound. After Isaac Newton. And the unit for mass is the kilogram, not the gram. You'd think it's the gram. Gram's too teeny. So what's standard is actually the kilogram, not the gram. So you got to keep that in mind, that the kilogram is standard, and working with newtons, you got to be in kilograms, okay? So before presenting these formal definitions, we're going to do a little experiment. All right. As we slowly increase the force on a given object. Wow, we got to hurry up so we can get done in 15 minutes here. All of the forces in newtons will become more standard. Oh, there it is. Somebody's in America. We're using the pound. All right, there it is, guys. A 4-pound force produces an acceleration of the wagon faster by 2 feet per second every single second. What happens with an 8-pound force? It's double the acceleration. That's what you'd have found in your lab. Triple the force, triple the acceleration, because it's the same mass of wagon. Okay, so acceleration is directly proportional to that force and the direction of the force. Friction, we're pretend there is no friction for right now. We're going to keep things simple. Okay. Alrighty. So what this experiment found, they're directly proportional. That if you double the force, you double the acceleration, and that change in force per change in A is a constant, because that's a constant slope. What do you think that slope would represent? Well, in this case, it's 8 per 4, which is 2. Okay? So 2 pounds per foot per second squared, whatever that constant is. So inertia or mass of one slug is 1 pound per foot second. Whoa! This would be 2 slugs right here. Not slug bugs, slugs. Not the gushy gooey things you find out in the garden. This is something different altogether you never hear of in your lifetime, because we don't really use the English system even for mass very much. But that's what we would call it. Okay, that's the constant, the amount of mass or inertia of something. If you have 2 slugs, which this is 2 slugs, this is twice the inertia or mass of what 1 slug would be. Oh, there it is. Mass is 2 slugs. There you go. Alrighty, so a measure of inertia. So 1 slug, you have a 6-pound force, makes it 6 feet per second squared of acceleration. What if you have 2 slugs? Well, it's half the acceleration. What if you have 3 slugs? That's a third of the acceleration. So 1 slug is the mass in which a constant force of 1 pound will produce an acceleration of 1 cubic foot per second squared. That's how you define what a slug is. Okay? It's the amount of inertia of something has at a 1 pound force will make it accelerate at 1 foot per second every single second. Alrighty. So we got the USCU system. So that's the American system now. Pounds and feet and seconds and slugs are the standard units on that. Okay? Alrighty. The metric system, there's where we're going to use the kilogram, seconds, the Newton, and the meter. Okay? Alrighty. So there you go. So if you have a 1 slug, it'll accelerate 1 foot per second squared if you have a 1 pound force, or 1 kilogram mass will accelerate at 1 meter per second squared if you have a 1 Newton force. There you go. This is where we're going to pause and start up all brand new on what the Newton is. Are you excited?